In Module 1, we established the baseline of a harmonic system. We defined an isolated core as an exact localized bound state, denoted as psi c. But local mathematical stability alone leaves a critical gap in the model. It cannot explain how physical mediation or wide area influence extends across space. To bridge this gap, unified harmonic systems relies on the field. In this framework, the field is never an empty medium, a vacuum, or a passive void waiting for particles to enter. On the left, the incorrect void model. On the right, the correct model. The field is a structured extension of the core through an already present continuum. A medium strictly refers to the local presentation of this overlap background, not a secondary layered substance. Modeling structural propagation through this background requires specific mathematical tools: rigorous mode decomposition, exact phase tracking, and matrix overlap constraints. Treating the continuum as an overlap background eliminates false vacuum assumptions. It forces a strict mathematical accounting of how a localized core projects true influence. To track extended field structure without collapsing the behavior into an undifferentiated aggregate, we use mode decomposition. This is the primary decomposition equation. It splits the full configuration field into two distinct components. The first component is the stationary bound core state, remaining anchored to the source. The second component isolates the continuous scattering modes of the local Hessian, representing the extended field. By enforcing this mathematical separation, the model isolates internal core persistence from the outward radiating interference. This 3D topographical chart compares an isolated core against a paired core system. The scattering modes governing these shapes are controlled by two modifiers: spectral amplitude and spectral phase offset. The complex interference ridges in the paired system are constructed using the exact same scattering mode vocabulary as the symmetrical isolated core. Mode decomposition calculates these interference topographies precisely. Downstream stability equations require these exact variables, rather than broad approximations. When these decomposed modes interact, we evaluate their combined behavior by deriving an effective frequency. This graph plots effective frequency using equation IIO2. Frequency here is not a context-free label. It is tightly bound to admissibility and phase relations. The equation integrates the spectral power and the local field mode amplitude over the entire frequency range to find the true spatial weight. This mode spectrum demonstrates phase relations. Minute phase offsets strictly dictate whether a local structure is reinforced into a constructive peak or suppressed into a destructive trough. Two field components can share identical frequencies, but if their phases are mismatched, they will fail to create any stable extended structures. This requirement introduces the noise floor as a hard validity boundary for the framework. This animation shows the noise floor threshold. Any fluctuation falling below this limit is assimilated back into the ambient background, rather than classified as a new physical mode. Filtering the noise floor prevents the mathematical model from overfitting local irregularities, generating false structural claims. Frequency and phase act as the ultimate operational filters. They determine when oscillatory alignment justifies stable mediation and when a mismatch guarantees instability. The climax of these field dynamics is the exact mathematical moment the field and the core connect. We call this the coupling handshake. This is the interaction energy integral, equation I203. It serves as the strict quantitative test for coupling quality, dividing the interaction into three critical terms. The first term is the spectral amplitude. The second term is the phase detuning cosine. The final term is the exact spatial overlap matrix element of the local Hessian. This illustrates the substrate fallacy. Many assume high amplitude guarantees interaction, but as we see here, massive waves pass directly through each other without binding. This diagram applies the coupling equation to a failed state. Because of severe phase detuning, the entire integral is forced to zero, completely nullifying the massive local amplitude. By contrast, an admissible attachment point requires the spatial overlap matrix element to perfectly align with the boundary phase. The local medium can narrow, skew, or fragment this usable coupling window, all without changing the underlying identity of the source core. Coupling is a spatial overlap and phase problem. The framework strictly forbids forming mathematical bridges based entirely on spatial proximity. Even with valid coupling, the entire field approximation model operates within absolute mathematical boundaries. This is the guardrail equation. It defines the maximum limits of the linear mode approximation. The integrated spectral power of the field modes must remain vastly smaller than the nonlinear Wistoring parameters of the primary functional. This phase space chart tracks the consequence of crossing that limit. The system abruptly moves from admissible field propagation into nonlinear structural breakdown. At this exact boundary threshold, the mode-based field approximation collapses, rendering the data invalid for downstream shell or bridge construction. Regime-specific conclusions generated in the stable zone cannot simply be exported into the failure zone. They require explicit, ground-up revalidation. The limit equation maps where the mathematical tools stop being reliable. This prevents fragile theoretical approximations from corrupting larger system-level predictions. Evaluating the total parameterization of the field radiating around the core yields a structure completely constrained by the rules of this module. This generates a final handoff block consisting of 4 data points: mode descriptors, interference class, coupling status, and regime limits. This specific data block is the uncompromising prerequisite for advancing to Module 3. Without this mathematically validated field matrix, constructing boundary shells and capture wells is computationally impossible. Module 2 ensures that the continuum remains a rigorous, mathematically bound domain. The field is now primed to host the topological boundaries of the next layer of reality. Evaluating the total parameterization of the field radiating around the core yields a structure completely constrained by the rules of this module. This generates a final handoff block consisting of 4 data points: mode descriptors, interference class, coupling status, and regime limits. This specific data block is the uncompromising prerequisite for advancing to Module 3. Without this mathematically validated field matrix, constructing boundary shells and capture wells is computationally impossible. Module 2 ensures that the continuum remains a rigorous, mathematically bound domain. The field is now primed to host the topological boundaries of the next layer of reality.